So, in our last class we were talking about the single stuck at fault model. So, today we first talk a little bit about the multiple stuck at fault model before going on to other fault models. Now, the multiple stuck at fault model, as I had mentioned in the last class, that here we assume that more than one line in the circuit can have a stuck at failure. So, any number of lines can be stuck at 0 or stuck at 1. Now, the point to note here is that the number of possible multiple stuck at faults are much higher as compared to single stuck at faults, which is, if you just compare, it is only 2k. The number of single stuck at faults is only 2k. In contrast, multiple stuck at fault is 3 to the power k minus 1. How this number is coming? You see, in a circuit there are k number of lines. Okay. Now, each of these lines can be in one of 3 states: good, stuck at 0, stuck at 1. So, there are 3 combinations in each of the lines. So, 3 into 3 into 3, it becomes 3 to the power k. And there is one combination where all these lines are good. So, you subtract that 1 from this. So, 3 to the power k minus 1. This is the total number of multiple stuck at faults which are possible. Now, as I had mentioned that since a test set which can detect single stuck at faults only can also detect a very large percentage of multiple stuck at faults. So, people usually do not consider multiple stuck at faults. Moreover, multiple stuck at faults have some problems which also need to be addressed, like one such problem is called fault masking. Now, this fault masking says that if more than one fault occurs at a time, then a test set to detect one fault may be invalidated if another fault is also present. Well, I will just illustrate this with an example. Let us take a simple gate level circuit. Say a 2 level NAND circuit. So, the inputs are A, B and C and the output is F. Okay. First, we consider a fault, say A stuck at 1. Now, in order to detect A stuck at 1, what is the test vector you need to apply? See, for A stuck at 1, you have to apply a reverse logic value to the line A. So, A has to be 0. This A has to be 0 in the first place. And in order that this, I am trying to detect A stuck at 1. So, in order that this possible change in the input propagates here, this has to be put to 1, because if this is 0, the output will always be 1. This means B has to be 1. Now, again the effect of the fault we are trying to propagate through this path. So, the output of this NAND gate must be at 1, because if it is 0, F will again always be at 1, there will be no change. So, in order to make it 1, C must be 0. So, to detect A stuck at 1, I have to apply this input vector. Now, suppose in addition to A stuck at 1, I have another fault which is also occurring, C stuck at 0. So, what I am saying is that if we want to also detect C stuck at 0, then the line C has to be put at 1. This 1 will make this line at 0, which will in turn make the line of F at 1. So, the fault A stuck at 1 will not be detected. So, this example shows that if two faults occur together, then we can have some faults which become undetectable faults. So, a fault F1 may become undetectable if a fault F2 also occurs in the circuit. Okay, fine. So, these are the most popular gate level fault models which people use. Now, we also sometimes consider transistor level fault models because of two things. Because number one, most of today's VLSI circuits are designed using MOS technology, they are CMOS. Number two, the MOS faults, they exhibit some peculiar behavior. There are certain kinds of faults which cannot be detected by the conventional single stuck-at fault test set. So, they have to be considered separately. So, let us see what these are. See, a transistor is sometimes also called a switch, an ideal switch. That is why these transistor faults are sometimes also called the switch level fault models. MOS transistor is considered as an ideal switch. Ideal switch in the sense that if you have a MOS transistor like this controlled by the gate, if it is NMOS, if the gate is at logic 0, I say that the switch is off. If the gate is at logic 1, I say the gate is on, it is conducting. Okay. It is just like an ideal switch. Now, the transistor level faults are of two types, stuck open and stuck short. Stuck open says that the transistor is never turning on. Whatever you are applying on the gate, it is permanently stuck in the open state. That means, the source and the drain, they are never conducting. Okay. Stuck short is the reverse. There is a short circuit between the source and the drain. So, a single transistor is permanently shorted irrespective of the gate voltage. Now, these two kinds of faults are peculiar. Peculiar in the sense that the stuck open fault, some of the stuck open faults cannot be detected by a single test vector. They will require a pair of test vectors for detection. This we will see why. And similarly, stuck short fault model sometimes may require the measurement of current from VDD to ground. Just by using any logic measurement, we cannot detect such faults. Okay. Now, let us see why these kind of peculiar behavior exhibit in case of a transistor fault. Okay. First, we look at the transistor stuck open example. Now, stuck open example, before I explain this, let me tell you one thing, that stuck open is interesting because this is an example of a 2 input NOR gate. Now, a stuck open fault can make a combinational circuit exhibit sequential behavior. Well, what I mean by saying sequential behavior is that the combinational circuit now behaves somewhat like a sequential circuit. This means that the output which you get in the present instance depends on the output which was there in the previous instance of time. This is not in the spirit of combination circuit, because in a combination circuit the output depends only on the applied inputs at the present point in time. Okay. So, let us see why this happens. Okay. This is the circuit diagram of a 2 input NOR gate. We assume that this pull up transistor is stuck open, this is always off. Well, here we observe one thing, this is an isolated gate. Now, this gate may be driving some other gate in the next stage. Some other gate means what? It will be driving the gates of some other transistor. It will be driving the some other gate like this. So, equivalently we can say that the output is driving a capacitive load, say CL, this is a load capacitance. So, you ignore these transistors. Now, equivalently you can say that the output has a load capacitance connected to it. This load capacitance is actually the gate to ground capacitance, gate to drain or source. Now, here suppose I want to test this transistor stuck at stuck open. Now, let us see what happens here. Stuck open means this line is always open circuit, right. Now, you just imagine a situation, suppose this A B are the inputs. Suppose I apply an input pattern which is say 1 0, as this shows A is 1, B is 0. If I apply 1 0, these are PMOS transistors. So, this will be off, this will be on, and one of the bottom transistors will be on. So, the output will be connected to ground and this capacitor CL will get discharged. So, the output C will be at 0. Okay. Now, suppose I apply an input say 0 0, then what will happen? 0 0. 0 0 means both the pull down transistors will be off, none of them are conducting. Both the pull ups were supposed to conduct, but since this transistor has a stuck open fault, this is open. So, now this output line C is like floating, it does not have a connection to ground nor it has a connection to VDD. So, current cannot flow. So, what will happen to CL is that CL will be holding the previous logic value whatever was there. So, in presence of the fault C will be 0 because capacitor was already discharged. This is in presence of the fault. Capacitor was already discharged, it remains discharged because there is no path for charging. But if this fault was not there, then when you apply 0 0, both these two transistors would be on and the capacitor would get charged through this path and the C value will be 1. Okay. So, here we can distinguish whether this fault is present or absent, but you try to think that if I had not applied the previous test vector, could I detect this fault? Because the previous test vector was applied with the sole intention that I wanted to discharge the capacitor to a known state. But if I simply apply 0 0, 0 0 means the output is open, but what will be the output value that I do not know, that depends on whatever was there previously. So, in order to detect the fault, I first set the output to a known state by applying 1 0 or I could apply 1 1 also. Then by applying 0 0, I am exciting this fault. Okay. So, this is one example using which I can detect a stuck open fault, but I have to apply two vectors in sequence. This is called two vectors stuck open test. Now, as I told you, a normal stuck at fault test set may not have these two vectors coming one after the other in sequence, but you can sometimes reorder the Stuckart tests by moving them up and down, so that this sequence appears one after the other, and using that you can detect many stuck open faults also. Okay. So, this is one peculiarity of CMOS circuits. The other one is the stuck short fault. Stuck short fault is different. Say this pull up transistor has a stuck short fault, which means there is a permanent connection like this. Now, if I apply a 1 0 input vector here, then well, under normal circumstances the pull up network would be off, pull down would be on, and we were expecting a logic value 0 in the output, because the output capacitor would discharge to ground. But since this transistor is short now, from VDD to ground there will be a current flowing path. So, this circuit will act as a voltage divider, there will be a high current flowing, and the output will neither be at logic 0 level nor be at logic 1 level, somewhere in between, it will be indeterminate. This kind of a thing cannot be simply detected by observing the logic value of the output. Rather, here you will have to measure the current that flows from VDD to ground. This is sometimes called IDDQ testing. You are measuring the quiescent current from VDD to ground, this is IDDQ. So, IDDQ testing or measuring this high current, sensing this high current flow is required for detecting such stuck short faults in MOS transistor. Okay. So, we have looked at some of the fault models that people normally use. In fact, we had concentrated only on the Stuckart and the transistor models, because they are more important from circuit design point of view. Of course, people also talk about functional and high level fault models, as I had mentioned, but we will not be discussing them as part of this discussion. We now move on to the problem of fault simulation. Well, now we have talked about the fault models. We know that which faults are to be considered. Now, fault simulation, what is this? This is a process whereby we create a model of a circuit on the computer. We also have the set of faults that need to be considered, that also is represented in the computer in some way. Then what we do, using that program, that simulator program, we find out that given a test vector, what are the different faults that are getting detected. Okay. So, the fault simulation problem and motivation are as follows. In the problem, we are given a circuit, typically a netlist of gates. We are also given a sequence of test vectors which you want to evaluate, and of course, a fault model. These are the three things which are given to us. So, what do you want to determine? We want to determine the quality of the test vectors. We want to determine a parameter called fault coverage. Fault coverage is the fraction or the percentage of the modeled faults which are actually detected by these given test vectors. Moreover, the fault simulation can also give you a set of undetected faults, for which you may have to generate some additional test vectors. Okay. So, fault simulation is useful in evaluating the quality of a test vector which you have with you. Okay. So, the motivation mentions that very clearly. You determine the quality of the test vectors. Now, since you are testing your product using this test vector, so if you can improve your test quality, your product quality will also get improved. And undetected faults, if you also find that, you can generate some additional test vectors to detect them. Okay. So, the typical flow is like this. You start with a fault set F. You generate the test for some fault in F. Well, you need not generate fault for all the faults in F. For example, this fault set F may contain 1000 faults. For example, there are 1000 faults here. You take any one of those faults and try to find out a test vector for detecting that fault. Why? Because if you carry out fault simulation after that, say this test vector was generated for a fault F1. Now, fault simulation will tell you that instead of F1, another 50 faults are getting detected by that same test vector. So, what happens is that although you have generated a test for a single fault, but the corresponding test vector is able to detect 50 faults. So, after this you can remove detected faults from F. So, now this set of 100 faults becomes 950. This process is iterated. So, the idea is that instead of iterating 1000 times, at each step you are reducing the number significantly, so that the number of times you will have to generate the tests becomes less. So, this fault simulation is typically used in conjunction with test generation in order to improve the quality of test. So, as the fault set F becomes empty or becomes very small, you can stop. This is the stopping criteria. Now, in practice there are a number of different techniques which are used for fault simulation. Broadly, the approaches which are followed can be categorized as parallel fault simulation, deductive, concurrent, and critical path tracing is of course a specific technique which can be used only for combination circuits, but the first three can be used also for sequential circuits with some modification. So, let us try to see briefly what these methods really are. Okay. Before going into the parallel fault simulation, let us first try to understand what simulation really means. See, we have a gate level netlist with us. Now, a gate level netlist, it can be represented on the computer as a graph. The gates are the vertices of the graph, the edges are the interconnections. So, representation of the circuit in a computer is not difficult, and also the node types have to be stored, which is AND, which is OR, which is NAND, and so on. Now, if we have some input which is applied, we have an input test vector. Suppose it is a 4 input circuit, I have 1 0 1 0 applied. So, on that graph, if we systematically trace from the primary input side towards the primary output side, we can evaluate the nodes one after the other depending on their type, and finally, we can find out the logic value of the primary output. Okay. Now, this is called true value simulation. True value simulation means in the absence of faults, if I apply these test vectors, this will be the output. Now, I can modify this simulation process a little bit. I can forcibly inject some fault in some circuit. For example, I have an AND gate somewhere, I say that the output of this AND gate is stuck at 1. So, if I keep this information then while I am evaluating that AND gate during the process of simulation, whatever may be the input, I will always evaluate the output as 1 because it is a stuck at 1. So, I can inject faults like this and I can find out the output value. For a given input test vector, if I see that my good or fault free output and the faulty outputs are different, then I can announce that this particular fault is getting detected. This I can repeat for all the faults. Okay. So, if there are 1000 faults, I have to repeat it 1000 times. Okay. Now, let us see what this parallel fault simulation means. This is a method to speed up the process of fault simulation. Here it says the good circuit and a fixed number of faulty circuits are simultaneously simulated. We will see how. So, means in the normal scenario, you can simulate only one circuit at a time. So, either you are simulating the good circuit or you are injecting a fault, you are simulating the faulty circuit. But here what I am saying that we are parallelly simulating the good circuit and W number of faulty circuits all together. Okay. So, if there are total of F faults, since we can simulate W number of faulty circuits at a time, so we would be needing F divided by W, ceiling of that, so many passes of simulation. Now, how we are doing this, means how we are simulating this in parallel. See, for this we are utilizing the inherent parallelism that is there in the arithmetic logic unit of the computer. See, ALU or the instruction set of a computer has instructions like OR, AND, XOR and so on. They do a bit by bit OR or bit by bit ANDing of the corresponding bits in a word. So, if it is a 32 bit word, I can have a 32 bit OR with another 32 bit number, bit by bit OR. So, I can utilize this bitwise logical operator to do this kind of parallel activity. So, we will show you how. First thing is that, okay, say we take a typical example. We have a computer with 32 bit word size. We take a 32 bit word. These are the bit numbers 0, 1, 2, 3, 30, 31. Okay. Now, what I do is that these 32 bits of a word, I assign some meaning to each bit positions. For each gate in the circuit, suppose there is an AND gate, I assign a word like this to the output of this AND gate. For each and every gate of the circuit, I have this kind of a word as. So, means in fact, this word will be assigned to each line in the circuit, not necessarily the gate output, there can be fan outs also. So, the significance is that, well, as a matter of convention, bit number 0 we will be using to indicate the logic value in good circuit. Bit number 1 we will indicate the value in presence of a fault F1. Bit number 2 value in presence of fault F2, value in presence of F3 and so on. So, what I say is that I am storing 32 bits or 32 values for the gate output at the same time, one of them will represent the good value and the other 31 will represent values in presence of 31 different faults, which means I am simulating 31 different faults at the same time. Okay. Now, let us see how we can do this. Let us take a very simple example and illustrate. Suppose I have a circuit like this. I have an OR gate, this is driving an AND gate, the output value is Z, this is X, this is Y. Now, this 32-bit word that I had said, there will be a word assigned to each of these X, Y as well as Z. Right now, we are concerned with the line Z. We will show you how we carry out fault insertion at the line Z. See, we will be systematically proceeding or carrying out the simulation from the primary input side towards the primary output. We assume that we have just reached this AND gate and we are trying to evaluate this, taking into account the additional faults on the output Z. Let us see how we can do this. Well, we maintain some data structure at Z, not only the word which stores the values, we have some additional data structures. Let us see what these are. First thing that we store, this is also a list. These are the bit positions. Okay. This is first the word which I am, this list that I am just talking about. Say, just I am taking an example. Suppose the first bit indicates the value for the good circuit, the second bit is the value for the fault X stuck at 1. Sometimes we also write like this, X/1 means stuck at 1. This is for say Y stuck at 1. This is for Z stuck at 0. This is for Z stuck at 1 and so on. So, X and Y stuck at 0 have been collapsed. So, they do not appear. So, there will be other faults in the circuit also, there can be some faults W, V lines like here, though they will also be there. So, I am showing some of the faults which you can see from here, but when you reach here you are more interested in the faults on the line Z, the output of this gate. So, this list we are calling I Z. There are some other data structures also I am showing you. There is another data structure called SZ, which will tell you that well this IZ is what. Okay, I am telling you what this means. This IZ is not exactly this list, rather it tells you that we are right now here, we are trying to inject a fault on Z. So, these are the two faults of our interest. So, the faults which are of interest now, I am setting those bits to 1, rest all are zeros. Okay? These are IZ, and SZ says that these are the two faults on the consideration fine, but first of them, first one is stuck at 0, the no, this is stuck at, sorry, this is stuck at 1 and the second one is stuck at 0. The rest all bits will be 0. Only these two bits are relevant. this 1 and 0. They will indicate the polarity of the stuck at faults on this line. Bit number 4 will indicate stuck at 1, bit number 3 will indicate stuck at 0. Okay. Now, the value of z you can calculate by taking simple AND of the list you have x and y. Suppose I have z value calculated as follows 0, 1, 0, 0, 0, 0. Now, the formula that we use is that you can calculate the new value of z dashed taking into account the faults at this particular site using a formula like this z and I z bar or I z and S z. The first one says I z bar means what? Other than these faults, all the other faults. So, ignoring fault on z, you take out only those 2 bit positions from z and retain all other bit positions as it is. For those 2 bit positions, you AND I z with S z, which is stuck at 1, which is stuck at 0, and insert it there. So, if you do this, z dash will become 0, 1, 0, 0, 1, 0. So, in this way, see, these additional data structures are used only for the purpose of inserting the faults, because as you go on simulating, faults on this particular gate will have some effect in determining that which are the positions that will need to be modified. So, this formula is used to make this modification, and in essence this is how the method of parallel fault simulation works, that you start from the primary input side, you go on systematically tracing the circuit from input to the output. At each line in the circuit you maintain this data structure, these lists, you manipulate the lists, you try to evaluate that what is the value you get for that particular output of the gate before you proceed to the next level, and you go on repeating this. Now, this method is all right, it works, but it has some limitations. Limitation in the sense, first thing is that this method works only if the circuit elements can be modeled using Boolean equations, because you are trying to utilize the inherent parallelism in the ALUs in the instruction set. So, unless you can map the basic operation into operations like AND or NOT, you cannot. So, you cannot apply if you cannot apply this scheme to slightly higher level modules like a multiplexer or a half adder, for example. It has to be only the primitive gates AND or NOT, XOR NOT. Okay. And second thing is that it is not event driven. Event driven means sometimes in order to speed up the simulation process, what we do, suppose we apply one input to the circuit, we simulate to evaluate the output. Now, we apply the next input. After applying the next input, we find that only in a small portion of the circuit there are some changes in the logic values. So, you only re-evaluate that part, the other part you do not re-evaluate, but in parallel fault simulation you will have to evaluate all the gates every time in means each of the passes, because in the same word you are encapsulating so many faults together. So, maybe for some of the faults it is not relevant, but for some other fault it may be relevant. So, we will have to evaluate all of them. Okay. So, this may lead to irredundant computation, and moreover you cannot take advantage of the so called fault dropping. Well, we did not mention this term, we just explained this, that as the faults get detected we remove them from the fault list. But in parallel fault simulation, because since we have already packed them in the machine words, we cannot very easily take them out from there. Okay. So, fault dropping is not possible, it is not event driven, and it cannot be used for higher level functional blocks. These are the drawbacks. Let us look at some other fault simulation techniques like deductive fault simulation. Now, deductive fault simulation is an interesting method. This is an event driven fault simulation in the sense that you only simulate a gate if some event occurs in one of the inputs. If there is no event occurring, then there is no need to simulate that gate. And unlike parallel fault simulation, you are not maintaining any words at the lines which store information about many faults. Rather, you maintain a set on each line, a set of faults which are getting detected. There is something called a fault list. So, you assign a fault list with every line of the circuit, and using some simple rules you propagate this fault list from the input towards the output side. So, let us see. The basic idea is you simulate the good circuit in the absence of faults. So, when you simulate the good circuit, you know the fault free logic value in all the lines of the circuit. From that, you try to deduce the behavior of all faulty circuits, and in the process you also try to deduce the different faults that may get detected. For this purpose, we use some data structure. The data structure is like this. You have a fault list Li associated with every line I. Now, Li, what is that? During simulation, the interpretation of Li is that this Li will contain the set of all faults that will cause the value of the line I in the faulty circuit to differ from the fault free value, which means if you have an AND gate for instance, and the good value simulation says that the output value is 0. So, the fault list for this output will contain all those faults which will result in this gate output value to be 1, the other value. Okay. So, you continue this process, finally you arrive at the primary output. So, in the primary output, the corresponding set will indicate those faults which will actually get detected, because those faults which will change the output value from the fault free value means those are the faults which are getting detected. So, we will explain how, but there is another important step in this method. This is called fault list propagation. Fault list propagation means you can have the output of a gate feeding some other gate. Okay. So, you have a fault list out here. So, this fault list may be propagated to the output of the next gate with some modification. There are some rules. Now, a fault list will get propagated provided one of these two conditions occur. First is a logic event. Logic event means, suppose you had applied say one test vector 1 0 1 1, for that you are doing this. Now, after you have done this, you have applied another input vector. Now, in response to this input vector, some of the signal values of this gate are changed. For example, this was 0, now this has become 1. So, if there is a change in signal value, we call it a logic event. Then you need to have a relook at this set, because some of the entries in this set may have to be changed. Similarly, there is another kind of event called list event. This says if the fault list of the preceding gate here there is some change out here, then possibly this fault list will also get changed. So, if either there is a logic event or there is a list event, you need to re-evaluate the fault list. Okay. Okay, now let us try to explain how this is done. Suppose I have an AND, let us take a simple example first. I have an AND gate A, B, Z. Suppose, well, this is an isolated AND gate inside the circuit. I am assuming that the fault lists LA and LB are already available to me. These are two sets. I am trying to find out the value of LZ. Now, under the present scenario, say the logic values are 1, 1 and 1. This is the true value logic. Now, you try to see that what will be there in LZ. In LZ, we will have all the faults which will change the output logic value to 0. So, actually what are the things that may change? First is LA, because LA the correct value was 1, if any of these occur it will change this value. So, LA means those set of faults which will change the line A to 0. So, this is one condition when Z can change to 0, or union LB, if B becomes 0 then also union a new fault comes in Z stuck at 0. So, if you have an AND gate with these applied inputs, then the fault list of the output will be, or it can be calculated like this. But let us take the same AND gate with same input fault list, say LA and LB, with say the applied input values 0, 1 and 0. Okay. Now, let us try to see under this condition how we will calculate LZ. See, this AND gate output is 0. So, LZ will contain all those faults which will make this 1. Now, let us see that how we can have this at 1. There are two conditions. One condition is that B will not change, B will remain 1, but A will change. Okay. So, A will change, B will not change. How do we write that? We write it like this: LA. LA means all faults here, it will change A, intersection LB not of that. LB not of that means none of these faults which change B, intersection of this, if there is anything common there, that can have this 1 1. This union, this additional fault Z stuck at 1. Now, LA intersection LB bar in set theoretic form, you can also express it as LA minus LB union Z stuck at 1. So, I have illustrated this process for an AND gate. You can similarly think and extend it to OR, NAND and NOR gates. The processes are similar. You will have to see the type of the gate and the applied inputs, and you will have to systematically trace it out. Now, let us take a bigger circuit and try to find out the fault lists. Let us take a circuit like this: A, B, this is D, this is E, and give some names to the circuit. Let us call this F, G H I J K and the output as Z. Okay. And let us say that we have applied the input vectors 0, 0, 1, 1 and 0. So, the true value simulation says AND gate output is 0, OR gate one of the input is 1. So, this will also be 0, 1, 1, this will be 1, OR gate will be 1, this will be 1. Okay. So, now if we try to systematically compute the fault lists starting from the primary input LA, A is at 0. So, LA will contain only A stuck at 1. Similarly, LB will contain only B stuck at 1. LC will contain C stuck at 0. LD okay, LD will contain D stuck at 0 and LE will contain E stuck at 1. Now, from these lists you can systematically go ahead with calculating the fault lists. For example, F, suppose I want to now calculate LF. See, this is an AND gate, output is 0. So, output can be 1 if both of the inputs change state. So, here the condition will be LA intersection LB. Okay. Now, LA intersection LB there is nothing. So, this set is phi empty. Similarly, you can find out LG for example. Well, LG will be the same, LG will be, no, LG will be, this is a fan out stem though. So, it will be LC, LC will be same, union an additional fault G stuck at 0. So, now it will be C stuck at 0 and G stuck at 0. Similarly, if you calculate LJ for example, LJ, what will be LJ? This is a NOR gate with one input at 0, other input at 1, 0. If you can, if you want to make it 1, you will have to make this into 0. So, this you can make how? This you can make it 0 by having a logic event here and not having, sorry, G, not C, it will be G, logic event here and not having a logic event here. So, it will be LG minus LF union the fault J stuck at 1. So, LG minus LF will be C stuck at 0, G stuck at 0, J stuck at 1. So, in this way you can systematically proceed till you will get some fault list in the output Z. So, whatever you get in the output Z, those will be the faults which are actually getting detected. Now, after this pass, when you apply the second set of input vectors, you do not throw away with the lists which you have already calculated. You retain them, and wherever in the circuit there are changes in the logic value, you recompute the fault list. And if there is a list event, you propagate that list event to the output of the next gate in sequence and you redo it. So, you will find that in the next step again you will get some other fault in the Z. So, there will be some faults will be detected. So, this is how this method works. Now, this method works faster than parallel fault simulation, but the problem is that the memory requirements in his is unpredictable, because the fault list can grow dynamically. You cannot estimate the total memory size for very large circuits. So, in general it may run out of memory for large circuits, and the method of fault list propagation which is used in this method it cannot take advantage of some technique called activity driven simulation, because this activity driven simulation, whenever there is an activity you are simulating, otherwise not simulating, that you really cannot take advantage of in this scheme. But as such, this scheme is a very interesting method. Just by maintaining the fault list and doing a true value simulation, you can find out all the faults which are getting detected in the output circuit. So, in this lecture we looked at some of the fault simulation algorithms. So, in the next class we will be continuing with our discussion in this regard. Thank you.